superposition in first order circuit. The total response is a superposition of the initial condition response with all independent sources killed, and the response to the independent sources with the initial condition killed. The initial condition response would mean the natural response. It would mean the transient response. It would mean the response when we are not taking into account the independent sources. Okay, so it is the superposition of the initial condition response with all independent sources killed, plus the response to independent sources when response to independent sources with the initial condition killed. So this would mean that, as we have done in the previous discussions, total response is a superposition of the natural and forced response. We need to find natural response, find the forced response, add both of them together, and then we have total response of the circuit with sources, with independent sources. Okay. In addition, the forced response is the superposition of the responses of each of the independent sources with all others killed, including the initial conditions. Okay, so this last phrase is very important. When you're now dealing with the forced response, which is the response based on the independent sources we have in a circuit, when you're dealing with that response, first of all, it will be the superposition of the response to each of the independent sources with all other sources killed. So probably if you look at this, you can try to find the response to this DC with this particular source killed, or you find the response with this current with this particular source killed. Okay, so and then you'll find this is the response you get here is going to be a forced response. So you could call this forced response 1, and then the response you get here will be another forced response. You could call this forced response 2. Adding both forced responses together give the total forced responses that we have. Okay, while you are killing one of the independent sources to get the forced response, you kill the initial conditions too. Okay, so this is how we're going to deal with this kind of problems. Let's get started with an example. You will get a better understanding of what we're talking about. So in this particular example, what you will find here is that we have 1, 2, 3 resistors on this circuit. Each of the resistors have different resistances. All right, and then we have, you can see we have a current source here. This is one of the sources. We have a voltage source here. All right, this is a voltage source here. Okay, you can see we have a dependent source here. So this is an independent source, this is an independent source, and these are the sources that we are going to kill. All right, and then we have an inductor here with 4/5 Henry. We have the values of our sources here, and then we have all of those parameters. Now, what they're asking us to do is to find I of t for t greater than 0. When time is greater than 0, what is I of t using superposition, where I of 0 minus is 2 amperes. When we say I of 0 minus is 2 amperes, what does this simply mean? It means that right before the switch is turned on, right before the switch is turned on or off, our steady state current is 2 amperes just before it is turned on or off. Okay, so and then after it is turned on or off, what we do have is going to be t greater than 0. First of all, we want to compute I due to initial conditions, and that would mean that we are looking at the steady state values. We're looking at the steady state condition. In that particular case, what we normally do in the steady state situation, we kill all independent sources. Okay, so we kill these. When we kill it simply means that we are opening the circuit. When you open this circuit, it simply means nothing is going on here. When you want to kill this, it means you are shorting this particular circuit. That's what it means to kill the voltage. So you can see here we are shorting the voltage source here, so we short the circuit. When you open this, nothing is going on here. All right, once you do that, it simply means 2 and 2 will then be in series, because all the current will pass through this place. All the current coming through this place will pass through this place. So these guys are going to be in series. So you can easily say 2 plus 2 will give us 4. Okay, so once you have 4 here, it simply means there and then that 4 will then be in parallel with 1. So you have 1 parallel 4. So when 4 is in parallel with 1, this is going to give you 4 times 1, right? All divided by 4 plus 1. So this will give you 4 divided by 5. So the effective resistance or equivalent resistance will be 4 over 5. That is why you have 4 over 5 ohms here. And then we have our inductor, which is 4 over 5 Henry. Okay, you can see that we have, so the current coming this way will now become initial condition current. Okay, so you want to label it initial condition current, or probably if you want, you could just label it I. But for the sake of identification, you could label it initial condition current. And then what we have left here is going to be 3 multiplied by V. Okay, don't forget, you will take note that these 80 volts and these 3 volts are 2 different things. Okay, this is 80 volts. This is 80 with the unit of volt. This is 3V. This is 3 multiplied by V. And you will know to find this V, you can easily, this is the V they are referring to here. This V that you have here, that is, the V that is also here. All right. So don't mistake this as 3 volts. This cannot be volts. Okay. This is 3V. All right. Let's go ahead. So if you apply KVL to this particular loop, what would you have? If you apply KVL to this loop, what would you have? Okay. So the first thing you want to start with, we are traversing from positive to negative, and then that would mean you have. So just look up here. That means you would have plus V, right? You have plus V. All right. And then if you go, you have plus 4 over 5. Okay. 4 divided by 5. All right. Now, the voltage across an inductor is usually given as L di dt. Okay. So that is why we have this 4 over 5 here. So di dt is what is left. So you put the I dt here. All right. So don't forget this I, we called it our initial condition current. Okay, so you could put IC there. So let me just put it there. The IC, the IC. Okay, let me not bother myself to put it there so it doesn't confuse it. But you know it is initial condition current. So we have 4 over 5 representing the L, the IDT, which is the voltage across an inductor or induced as an inductor. Then plus 3V would be the next voltage that we would have. If you add everything together, it should give us 0. That's the way this is expected to operate under normal circumstances. Okay, so you see we have plus V plus 4 over 5 the IDT plus 3V equals 0. Again, what you will find out here is that finding your V is not going to be difficult because we already know that the current passing through there is just going to be the I initial condition current. And then we do know that the resistance is 4 over 5 ohms. So according to Ohm's law, your V would be equal to IR. All right. So R is 4 over 5. So you can see that you can easily say that your V would be. So using this equation that I wrote in blue, that we created in blue here. So what you find is that your V would be 4 over 5 multiplied by I. So this V here is 4 over 5 multiplied by I according to Ohm's law. So you have 4 over 5 multiplied by I, where our I is actually supposed to be, the initial condition current. So that is how they got this 4 over 5 you see here. Then plus, of course, we have another 4 over 5, the I, the T. So probably I should use capital I here, the I, and then I can use initial condition, the IC, okay, cool. The T, you're gonna have that here. Then plus 3V. Okay, so you can have it as plus 3V over there. All right, now instead of you writing plus 3V, what you could write here is plus 3. All right, and you know that our V is 4 over 5I, so you can write it as plus 3 multiplied by 4 over 5I. I hope you guys are following, and then everything here is going to be equal to 0. This is V, 4 over 5I is V, okay, so, and this is 3V, so we just replace that, and this is also V. If you expand all of these here, 4 over 5I plus 4 over 5 the I, the T plus 3 times 4 over 5I. This is going to be 12 over 5I plus 4 over 5I. So this automatically will give us something like 12 over 5I plus 4 over 5I will give us 16 divided by 5I. All right. So this will be plus 4 over 5, 4 over 5. And we still have our the I initial condition, okay, T equal to 0. So if you have it this way, everything, you know, should be more straightforward from here. Now you have 16 over 5 plus 4 over 5. All you need to do is just multiply all the sides, all the sides we have by 5 and divide by 4. So if you multiply all the sides by 5 and divide by 4, what do you get? Okay, so that would mean that you have something like you multiply this one by 5 over 4. Okay, you also multiply these by 5 over 4, okay, times another 5 over 4 here. Okay, and then you can also multiply these by 5 over 4 to keep the identity of the equation. So we're multiplying all the sides by 5 over 4. Eventually, everything here will still be 0. Okay, so that is why we're still going to have 0 here. And then here, 5 is going to cancel 5. 4 is going to cancel 4. So what you're going to be left with is just going to be the I initial condition, the t, which is what we have here. The I initial condition, the t. That is all you have here. And then here you can see that 5 will cancel 5, and all you have left is going to be 4 here is 1, and then 4 here is going to be 4. So you are left with just 4i here. That is how they got this 4i with the initial condition here, which will be equal to 0 because this is also going to be equal to 0. Okay, so they broke this down right from here down to this place. Okay. Now, what you will find out here is that right from here, you're going to obtain two expressions, okay? And those two expressions will be in this particular format. You would obtain, if you solve this properly, you would obtain sk exponential minus st, and then you would have these. The way this is going to appear, you have it plus 4k exponential minus st. Okay, you would have all of those equal to 0. This is how to find the natural response, because you would assume the solution for the natural response for these. If you assume that solution, you will, that means you're assuming that your NIN, which is IN natural response, will be equal to K exponential S. Okay, that's what we're going to be assuming. So if you have that, this is supposed to be ST, right? Okay, so this is going to be K exponential ST here. And then you have another k exponential st here. So eventually what you're going to have is k exponential st, and then you have s plus 4 equal to 0. Okay, if you remember how we do our quadratic expression, so you have this in bracket. So it's either this is equal to 0 or this is equal to 0. You equate both of them to 0, you get two different values. Okay, but then from our explanations, we saw many examples like this. K exponential st cannot be equal to 0. So if k exponential st cannot be equal to 0, by definition, it simply means that only s plus 4 will be equal to 0. And in that case, s plus 4 will be equal. So that means s will just be equal to minus. S will just be equal to minus 4. All right, that's what it simply means. So that is exactly how they got this s equal to minus 4 here. All right, so if you understand me right up to this particular point, it simply means that you're doing really good, and then we can take it a step further. We can then go ahead and say we have I of 0 minus equal to 2a. This will be the same thing of I of 0 plus, by the way. By definition, this would also be equal to I naught. All right, so this would mean we have this, and everything is going to be equal to 2 amperes. All right, that's given here. So they equate everything to 2 amperes. All right, and then you equate, if you equate it to 2 amperes, don't forget that we already said that our S is equal to minus 4. If S is equal to minus 4, it simply means that our I would be equal to k exponential st. Okay, and s is minus 4, it becomes minus 4 minus 40. This is what we're going to have here. Okay, so and this is going to be I natural, by the way. IN, you want to call that I natural. All right, equal to k exponential minus 40. Okay, and then we said this is going to be equal to 2 at t equal to 0. This is going to be equal to 2. So if you have it like this, it simply means when t is equal to 0, you can also put 0 somewhere here, and everything at the top here would be 0. So you have k multiplied by 1 will give us k, and then k would naturally be equal to 2 if you have that. So if your k equal to 2, you can then go back and say, and just put k here, and then say that our I natural is just going to be 2 exponential minus 40 I natural represents our I initial condition. Don't forget that. Our I natural represents our I initial condition. Okay, so that is exactly what you do have here as the value of your current. Okay, if we take it a step further, what do we have? Now that we have found the natural response or the initial condition response after cleaning all the sources, the next thing we want to do right now is to find the forced response. Now, compute the first component of IF1 due to independent voltage source. Okay, so we kill the initial conditions and all other independent sources on the circuit, irrespective of how many they are. You will find out that we have two independent sources in this particular circuit. There may be circuits where you have more than two independent sources, but in this particular circuit, we have two independent sources. Okay, so that is why we're going to find IF1, we're going to find IF2, add both IFs together, and then we know we have the total force response. So in order to do that, what you find out here is if you kill the initial condition and at the same time kill the other sources, what you're going to find out is that there is the current source is no longer appearing here. Why? Because we killed it. We want to find force response due to just this voltage alone. So we just kill this one. All right. So once you kill this one, this is what the circuit is going to look like. You're going to have two loops. So you can create two loops and say this is going to be loop 1, this is loop 2. You have your 80 volts, you have your ohms here. Okay, and then you have 4 ohms here. Where is this 4 ohms from? This 4 ohms is from here. Okay, so once you kill this, you're going to have 2 plus 2 here is going to be 4 ohms, and this 4 ohms is going to be in parallel with this here. Okay, so you could draw it here, you could leave it here as 4 ohms, or you could just draw it here, as 4 ohms. But in this case, we chose to draw it here as 4 ohms. We have our Henry, 405 Henry here, and then you have second loop 2 here. Okay, so with this, all you need to do is just take KVL for the 2 loops that we have. So KVL for the first loop will give us minus 80, because we are traversing from negative to positive here, minus 80 plus 1 times I1, because the V here would be, the resistance 1 multiplied by this I1. So you have I1 plus 4. Okay, so this is going to be I1 minus I2. So current here minus current multiplied by 4 will give us a voltage. So we've got this, we've got this, we've got this, and then we go on and say, you equate everything to 0, because that's all the stuff we have in this particular circuit. So if you evaluate all these, you expand, and then you rearrange, what you have left is 5I1 minus 4I2 equal to 80. So you keep this somewhere, and then you go to mesh 2. All right, you take KVL again for mesh 2. What you find for KVL for mesh 2 is that if you start from here, you have 4 multiplied by I2 minus I1. Don't forget our notations, our polarity, and sign conventions. 4 I2 minus I1 will give us a voltage across this 4 ohms, plus the voltage here will be L di dt. Okay, so it will be L di I2, L is 405, then di the t. Okay, in this particular case, we have an I2L. You could call it IF1 if you want. You could call it IF1 if you want. Okay, so or you could just call it I2, because this IF1 will be equal to I2 because we have labeled this as I2 by the way. So IF1 will be equal to I2. If you like, you could use IF1 directly. All right. So you have that, then plus 3I1. All right. So how did we get this 3I1 here? That's the next question you want to ask yourself right now. How did we get this 3I1 here? Don't forget I told you guys that the V you're looking at here is not volt. This represents V, okay? It represents V, all right? So if you look at what we do have here, our I1, to find this V would be equal to IR, right? The I is I1, the R is 1. So I1 times 1 will just give us I1. So this V is going to be equal to I1 because resistance is 1, and then we have I1 here. So that is how we got this V equal to 3I1 here. All right, you just replace the I1, the V with I1 equal to 0. If you rearrange that, this is exactly what you are going to get as your equation 2. This is also pretty straightforward. All right, now substitute I1 from 1 into 2. Substitute I1 from 1 into 2. So what you would have here is, the reason we are substituting for I1 here is because we need I2. we need I2 because I2 is what will give us our IF1. So we cannot substitute for I2. I2 is what we're looking for. So that's why we're making I1 the subject of the formula and put it in equation 1. So if you do that, if you do all those substitution, what you would obtain is this equation: 4I2 plus the I2 dt equal to 20. That's what you do. Okay, and this kind of equations, this is like first order differential equations. It's going to have two solutions. It's going to have the particular solution and then the characteristic equation. The characteristic equation is also can also be called the homogeneous equation. All right, so to get the particular equation, to get the particular solution, what you say is that let the solution I2, let I2 be equal to any arbitrary value. You could call it A. Okay, so that's what they did here. So if I2 is equal to A, what do? You put A here. It becomes the A to T. If A is just an arbitrary constant, it simply means when you're differentiating a constant, the A to T will be 0. Okay, so everything here becomes 0. All right. So, and then you have 4A left here because you have assumed IA equal to 2. This is like a trial solution that we have here. So we have 4A would be equal to 20, and then A would be equal to 20 divided by 4, and then your A would be equal to 5. That's how we got here. All right. Now, after obtaining that, you want to find your homogeneous equation, your characteristic equation. Again, how to deal with this is going to be very easy. All you need to do, first of all, is you assume your solution is equal to k exponential st. You assume you assume a solution, okay, is equal to exponential k exponential it. This is st. This is, you assume this solution k exponential st. Okay, so if you assume this solution and then you put it in here, you put that here as d of k exponential st here. You have 4k exponential st here, and you rearrange it. You're going to have two solutions, okay, and both of them are supposed to be equal to 0. And we said this is going to be one of the solutions, and this cannot be equal to 0. The only one that will be left that you can equate to 0 will be 4 plus s. Would be the only one that you can equate to, like I did the other time. Okay, so by now, once you get used to these kind of expressions, when you see something like this, you automatically know that the homogeneous equation will be 4 plus s equal to 0. You can't equate it to 20, okay, because we're dealing with homogeneous characteristic equation. You can't equate it to 20, it will be equated to 0. So you have 4 plus s equal to 0, and then your s will be equal to minus 4. When your s is minus 4, then this becomes k exponential minus 4t. All right, since you found your s with minus 4, the solution here will be k exponential minus st. So we found one solution, I equal to a, where a is 5, which is here. So that means our I2 equal to a, and then we also found another one to be I equal to k exponential minus 4t. So adding these two together will give us the total I for this particular situation. Total I, total response of the voltage when we kill the initial condition and kill the current source, the independent current source. So total I2 of t will be equal to addition of these two responses, A plus KE ST. KE ST is same thing as KE minus 40. A is 5, so you have 5 here. So you keep these here. Again, you go back to the conditions that we do have. Now we have killed the initial conditions, right? Because we need to find the value of the K. We have killed the initial conditions. And once the initial condition is killed, it means your I2 of 0 plus in this case would be equal to 0 because we're dealing with I2 right now, or IF1. Okay, so I2 of 0 plus will be equal to 0 because we killed the initial conditions already. So if you equate everything here to 0, that means this is going to be 0, right? So equate everything to 0. All right, what you will find, and then this is going to become 0. So you have k exponential 0, k plus 5 equal to 0. So your k automatically will be equal to minus 5. So once you get your k to be equal to minus 5, that simply means you can easily put that here. So you then have I2 of t will be minus 5 exponential minus 40 plus 5. You can easily rearrange that and it becomes 5, 1 minus exponential minus 4t. So this is the response you get. This is the first response you get when you when you kill the current source and then you try to find the response based on the voltage source. Okay, so this is what you get. The next thing we want to do right now is to kill this voltage source and then find the response of this circuit based on the current source. That's the next thing we're going to do right now. All right, so let's try to do that. In your mind, you already know exactly what we are going to do. We're just going to repeat the same procedure. That's what we're doing right now. We're just going to repeat the same procedure we had right up here and then see exactly how that plays out. So compute the first component IF2 due to independent current source, kill the initial conditions and the voltage source. Okay, just the same thing. So if you do that from the main circuit, the only thing you won't see here is the voltage source, will take it away. So you have our current source here, you have our 2 ohms here, you have 2 ohms here. So you create 2 loops. So you have a loop here and then you have another loop here. For loop 1, mesh 1 rather, what you do here is that you have, so you have minus 3V, all right? In this particular situation, what would be our V, all right? What would be our V? V would be equal to IR according to Ohm's law. IR, our R is 1, the I would be I2 minus I1, all right? The I passing through this 1 ohm resistor would be this I2 minus I1. I1 is coming down, I2 is going up. So it's going to be I2 minus I1 multiplied by 1. That would be equal to V. So this 3V here becomes minus 3 times that V, which is I2 minus I1. That is how we got V here, okay? Then we move on again to say that here the voltage across the across the inductor would be L dt. L is 4 over 5. Okay, this is 4 over 5. Then we have the I1 dt because we have defined the current passing through here as I1. All right. So you have I1. So you have the I1 dt plus what can you see here? Plus V here. Okay, so we have passed through here and then we get here plus V. Again, V will be equal to I1 minus I2 because the current here is coming down and then our current here is going up. So you have I1 minus I2 multiplied by 1 will give us the voltage here. All right. Now you add everything together and then you equate to 0 according to KVL. What you would notice here is that our IF1 in this case is not going to be equal to I1. Why? Because they are in opposite direction. So our I1 would automatically be equal to minus IF2. Whatever we get as our I1 would be negative of it would be because they are in opposite direction. So I1 would be equal to minus IF2. I just wanted to point that out before we continue. All right, so let's go on. We know how we got this, we know how we got this, we know how we got this, we equate it to 0. So if you rearrange all those, this is what you are going to obtain. If you rearrange that equation, you obtain equation 1, and this is what you have. You just expand these, rearrange it, and then you have these. All right, then you go to mesh 2, the same thing is going to happen. You have I2 minus I1 for V here, multiplied by 1 to give you the voltage across 1 ohms here, plus 2I2, as you can see here, because I2 will keep going up here and it will pass through this place, then plus another 2, the current will continue to this place. So the current passing these 2 ohms here, these guys here are in parallel. So if this current is coming this way, it's coming this way, okay? So it will be, this current is passing through here, this is also passing through here. So it's just going to be I2 plus 10. That's why you have I2 plus 10 here multiplied by these 2 to get the current passing through these 2 ohms, okay? So if you expand all of these, this is what you're going to obtain. You would have this expression, equation 2, if you expand this particular bracket, okay? And then you rearrange them. So you have equation 1, you have equation 2. Again, what is important to us here is I1, because I1 is what we're going to use to find our IF1. So you want to substitute for I2 here. So from equation, substitute for I2 from equation 2 into 1. Okay, so we want to eliminate I2 right now. So you make I2 subject of the formula in equation 2, put it in equation 1, whatever you obtain. In the final analysis, you are going to find out that you obtain the I1 dt plus 4I1 equal to minus 20. That's what you're going to obtain. Once you carry out all those mathematics and you do all those substitutions, what you're going to obtain is going to be the I1 dt plus 4I1 equal to minus 20. Again, once you obtain this first order differential equation, the rest becomes very easy. First of all, you need to find two solutions, the particular solution and the characteristic equation, or the homogeneous equation, as the case may be. If you want, you can say again, to find the particular solution, you can say let I1 be equal to A, because you need to find a natural, assume a trial solution for I1. Okay, so you say let I1 be equal to A, or let it be equal to B, or any constant that is okay for you, that is not going to confuse you. In this particular case, because we've used A before, we said let I1 be equal to B, okay, because we've used A before. So we said let I1 be equal to B. So this becomes 4B, and then this becomes dB dt. B is a constant, so d dt of a constant, that means you're differentiating a constant, that gives you 0. So everything here becomes 0 when you're differentiating. So you're left with just 4B. Let me say that. So you're left with just plus 4B equal to minus 20, and B would be equal to minus 5, because you have minus 20 divided by 4 eventually. Okay, so B would be equal to minus 5 at the end of the day. Once you get B to be minus 5, the next thing you want to do is to find the characteristic equation. To find your characteristic equation, from here you already know that what you're going to have is 4s plus 4 is what you're going to have here, equal to 0. You're going to have s plus 4 equal to 0. This time around, you want to equate it to 20, because you're looking for the characteristic equation, all right, without this constant here. So once you do that, you have your 4 plus s equal to 0, and then your s will be equal to minus 4. Once you have that, it simply means you have got two solutions. If you add both of them together, you will get the total forced response when you kill the voltage source and you only keep the current alive, and of course you also kill the initial conditions. Okay, so you have, what you have is I1 of t will be equal to k exponential minus 40 minus 5, because you got your s to be equal to minus 4. So that comes here automatically. What else do we do here? We need to find the value of k. Since we kill the initial conditions, I1 of 0 plus would also be equal to 0, because we already killed the initial condition. Otherwise, we would have said it's equal to 2 based on what they gave us, right from the beginning of the question. But we have to kill the initial condition here too for this superposition theorem. So I1 of 0 plus will be equal to 0. If you equate everything here to 0, that simply means you can easily say that your t is 0. If you put that here, everything here becomes 0. So you have k would be equal to 5. So that is how we got k to be equal to 5 here. So if k is equal to 5, what does that mean? That would easily mean that you can then bring the k here. So it becomes 5 exponential minus 40 minus 5. If you rearrange that, don't forget I told you that I1 of t will be equal to minus IF of t, because of the direction of flow of current for both of them here, direction of flow of current here. So I1 of t will be equal to minus IF2 of t. So eventually you would obtain these as 5 exponential minus 40 minus 5 as your minus, okay, let me make it this way so it will be easier, as your minus IF2. This is what you have here. Okay, so minus IF2 of t equal to this. That simply means that if you were looking for IF2, you just multiply everything by minus, so it becomes plus here. This becomes plus here, and this becomes minus. So this is what you have as your IF2 at the end of the day. So don't forget, we have IF1 now, we have IF2, and what we're looking for is for the total IA, total forced response is what we're looking for. So total forced response will therefore be equal to the summation of all the forced responses. You add all of them together. Summation of all the responses, rather. Okay, we have all the forced responses, and then we have the natural response. So the total response in the entire circuit would be the natural response plus the forced responses that we do have. Okay, so the forced responses are here, and then the natural response is somewhere at the back. Okay, so if you bring everything together, this is what we are going to have at the end of the day. So using superposition, your total response, I of t, will be equal to the initial condition response or the natural response, or probably you want to call it the transient response too, plus the forced response 1 plus forced response 2. All right, if you add all of those together, it gives you 10 minus 8 amperes. If you add all of those together. All right, now what I want you guys to pay attention to here is very straightforward and easy. It is possible you will find out that we have, how many forced responses did we find? We found a natural response. You know, that was where we started from. Then we found two forced responses. Okay, and the reason we found two forced responses is because we had just two independent sources here. Okay, you see, we have just two independent sources. Okay, if peradventure you have a circuit where we have three independent sources, it simply means that we are going to have three forced responses. Okay, if you have four, so the number of independent sources we have will determine the number of forced responses we would find before we eventually add all of the forced responses together to make one, and then add the natural response to find the total response in the circuit. All right. Now we want to briefly talk about unit step function, the pulse function, and then we'll try to solve some examples about that, and then we'll go straight away to the second order circuit. So unit step function. What you will find here is a function, is a graph. So you can see you have u of t here, you have 1 here, and you have 0 here. And when you say unit step function, a unit is usually represented as just 1. A unit is represented as just 1. So when you say unit step function, it simply means that you're saying that you have a function that is 1. You can see here you are either 0 or 1. All right, if it's going to be more than 1, probably it's just going to be in a step of units, 1, 1, 1, and so on and so forth. So you have a unit step function here. U of t would either be equal to 0 or be equal to 1. When t is less than 0, when your time is less than 0, it simply means that your u of t is 1. This is what this graph interprets. So what you see here is that this is t, this is 0, so this is plus here, and this is the negative part here. So when t is less than 0, that means we are going this way. And when that happens, it means that our u of t, as you can see, is on, our u of t is going to be 0 here, because our t is less than 0. So u of t is 0, right? For all values of t less than 0, that is what your u of t will be. It will be 0. Again, when your t is greater than 0, what would be our u of t? Now, this is values of t greater than 0 to this direction, positive values of t. What you will find out is that at that particular point, immediately t is greater than 0, u of t rises to 1. And at that particular point, for all values of t greater than 0, your u of t would be 1. This is why we call this a unit step function. Okay, so when t is less than 0, u of t is 0. When t is greater than 0, u of t is 1. So you see that we just, juggling between 0 and 1. All right, what if we have another function? But before we go into that, I'm just going to briefly explain a couple of things to us. Okay, now this is a voltage step source. What we usually have here, you can see we have v u of t here. This is a voltage step source. All right, this is the usual configuration we're familiar with. Now this configuration is equivalent to this particular configuration. All right, so you can see we have our switch here. Okay, you can see, and then this can be withdrawn like this. Okay, so this is going to be now our DC volt, okay, that we are familiar with, and then this becomes our switch. All right, and then you can see we have VU of t here. This is, you can see there is an addition here. All right, so pay attention to that. Again, the same thing is going on here. When you have a current step source, IU of t, the step source are usually represented with this U of t here. Okay, so this is current step source, and this is voltage step source with VU of t. Current step source is IU of t. This will be equivalent to the circuit you have on the right hand side here. You can see here we have IU of t moving this way. You can see we have our switch here, and then you can see we have this is also added here. This is very important. So you should be familiar with this configuration. What happens when we have a shifted unit step? Okay, when the step is shifted, initially we had said that t is equal to 0. So if we shift it and we say t moves from 0 to t naught, all right, what would be the value of our function? All right, so it simply means that we are looking for an area under this particular graph. All right, initially we were looking for an area from t greater than 0. All right, so this area will be all the values greater than 0. All right, so we could find the area under this particular graph. And looking for t less than 0, we know that everything rests on, u of t equal to 0. But in this particular case, if it shifted from 0 to somewhere, it shifts from 0, let's say t naught. So it simply means that for t greater than 0, this is now the area that we are focusing on. All right, for t greater than 0 here, this is now the area that we are focusing on. So what you find out is that there's been a shift from 0 to t naught. Our u of t, this becomes u of t minus t naught. All right, so this time around you can see the limits have changed. Here we have t less than t naught. So that simply means for t less than t naught, our u of t minus t naught will be equal to 0. That will simply means. Again, that is why you can see that on this flat end here, t less than 0 here, some part of it will be positive while the rest will be negative. But whatever it is, u of t minus t naught will be 0. Okay. Then for t greater than 0, that's going to be starting from here right up here. All right. Starting from here right up here, you find out that your u of t minus t naught also is 1 up here. Okay, so we move up here for a unit step function, for a shifted unit step, and then this is going to be the area we'll focus on. All right, so here is a simple analysis. Sketch v of t equal to ku of t plus ku of k2 u of t minus t naught, where both k1 and k2 are positive. So when you have these, what do you have? So our usual k1 u of t, we know what this means because k1 represents just a constant. So you know what this means. When you have u of t, this is what it means. K1 could be anything. It could be 1, 2, 3, 4, 5. It's just a constant. It could be anything, right? So basically, what you will find out here is that the coefficient of this u of t is what represents what we have here. All right. So if you go back here, what you will find out is that the reason you have 1 here is that the coefficient of u of t here is just 1 multiplied by u of t. So you can see the 1 here. All right, I'm just showing you some of those things because they will help your understanding. All right, let's go on. So what you find out here is that we have k1 here. Okay, so k1 u of t will be equal to this, and then of course k1 u of t will be equal to k1. Before now it used to be equal to 1 because we just had 1 here. So now that we have k1 u of t here, so this becomes k1. For t less than 0, k1 u of t will be equal to 0. For t greater than 0, k1 u of t would be equal to k1. Okay, so you have this played out. Then for k2 u of t minus t naught, we also have a representation of these. So what you see is that there is a shift here to the right. Okay, so we have a t naught here. So t minus t naught gives us an area here, that area of interest here. So first of all, k2 u of t minus t naught will be equal to 0 for all t less than t naught. So starting from t naught here down to the negative axis of t, or k2 u of t minus t naught will be equal to 0. And then it will be equal to k2 u of t minus 0 will be equal to k2 for t greater than t naught. Okay, because that will be like a step function from here. So it goes up here to k2, and then it means constant for all the values of t greater than t naught, right? So this is what we do have. So what we're trying to do is now to add these two together. That's what we're trying to do. Okay, so you find out that at k1, this is what we have. You can see here at k1 we're going up here, all right, and then at k2 you can see at k2 we move to this side before going up. Okay, so and that simply means our t is no longer 0. T is now t naught. So right on top of t naught, if we trace this down here, right on top of t naught, you can see we can just have our k2 go up like this. So what we have here is not just going to be k2, all right? It's going to be k1 plus k2, because we're starting from 0 to k1, and then from k1, okay, so this here to here is k2, but at this particular point, what we're going to have is going to be k1 plus k2, okay? At this point, we have 0. At this point, we have k1, because this is going to be k1 plus the initial, which is 0 here. So k1 plus 0 is what we have here. That's why we just have k1. So this is k1, but we do have k2 here, the shift of k2 here. So what we have here will be k1 plus k2 is what will give us the final value we have here. All right, and that remains that way for all t greater than t naught. So what you see is that we have t less than 0. When you add both of them together, we have 3 limits. We have t less than 0, and that starts from here. We have t greater than 0 but less than t naught, so that will be between here. You can see that t greater than 0 but less than t naught. At that particular point, the v of t would be equal to k1. I mean, this v of t, which is the summation of these two, when you add them together, it will be equal to k1. And then for t greater than 0 will now be from here, all the values greater than t naught, okay, right up. You can see that here, and then what you have is going to be k1 plus k2 will be equal to v of t. Okay, so here is another analysis here. Sketch u of minus t. So what you can see here, you can see we have a reflection here now. It used to be u of t, all right? So we have it. We know what u of t looks like, okay? We have these, and then we'll go up here, and then we go here, all right? And then this becomes 1 here for u of t. Now that we want to have u of minus t, what does it mean? It simply means that we are reflecting t. In this particular case, our t goes, this way. This is our t, so we're going this way. So now when we say we have u of minus t, what does it mean? It simply means that our t is going this way. So you know exactly what the graph would look like, okay? So I'm going to show you right now. It simply means that the unit function is not constant towards t, it's constant towards minus t. That's what it simply means. From 1, it goes this way. So for u of minus t, it's like just reflecting u of t, okay? So you can see when t is less than 0, this is what you have, minus t this way. So you have u of minus t will be 1, and then it keeps going that way, okay? What about u of t minus u of t minus t naught? Okay, so in that case, what do you have? Well, what you would find out is that, first of all, u of t, this is u of t, this is u of t, and then again, we want to find u of t minus t naught. Okay, so if this is u of t going this way, and then we usually have our t naught somewhere here. Let's say this is our t naught. Okay, so u of t minus t naught. Okay, what you see here is negative, right? Sorry, this is negative here. So that means that u of t, excuse me, yeah, negative here. So that means that we are reflecting t minus t naught, okay, to the left. We are reflecting it. So u of t minus t naught would be coming, you just from t naught this way, you go this way, okay? So that simply means that you create a pause function. This is a pause function, by the way, okay? So you have these here, you have these here, and then you have this pause here as a pause function. So this is a reflection of u of t minus t naught. This is u of t that we know, and then combining both together gives you this pause function. So let's briefly look at this definition. The voltage or current response of a circuit having only one independent source, which is a unit, either voltage or current step function, is what we refer to as step response. So what you find out here is that if you have a circuit and that circuit has more than one independent source, this gives you the motivation for the killing that we've been talking about. You kill every other source until you have just one independent source, and then you deal with that problem, that circuit with just one independent source, you get that response. And then, so when we have just one independent source, and then we have a response that is a unit, either voltage or current, we refer to that kind of response as step function. There is no initial energy stored in the storage element until t equals 0, unlike the previous analysis that we've had, where you already have initial charge, before you turn the switch on. All right. So in this case, there is no initial energy stored in the storage element until t equals 0. Then that will take us to the next explanation, which is going to be the pulse response. It is a response to a single pulse. The response to a single pulse is what we refer to as a pulse response. And then during the pulse, the response is identical to a step function or a step response. After the pulse, the source goes back to 0, and the initial conditions for this is set right before the trailing edge. Okay, so in general, a pulse is an example of sequential switching. A sequential switching problem can be solved by dividing the analysis into time intervals corresponding to specific switching positions. And we're going to use some examples to explain all of these. So here is an example. Find the step response of the following circuit and sketch it. Find the step response of the following circuit and sketch it. What you can see here is that we have just a single independent source here, and you can see our VG is equal to U of T volts. All right, you can see we have the resistance here. We can see we have our capacitance here. Okay, and the charge on the capacitance is V. All right, so you have these, and we want to find the step response. Okay, now this is what you do here. First of all, you want to, we know right from the time that our V of 0 minus would be equal to 0. We said that because we said that storage element is only charged when T is equal to 0. Don't forget we said that. Okay, so it simply means that, let me take you back to the explanation I just gave. From this explanation, we said that there is no initial energy stored in the storage element until T equals 0. So before T equals 0, it simply means that V of 0 minus, that before T equals 0 will be equal to 0 because there is no initial charge at all. So V of 0 minus would be equal to 0, and then V of GT would be equal to 0 because T less than 0 will make that so. So for all values of T less than 0, our volts, our charge, the element will be charged to voltage 0. So by continuity principle, it simply means that our V of 0 minus will be the same thing as V of 0 plus, which will be the same thing as V of 0, and that would be equal to 0 volt for continuity, application of continuity principle. Okay, so if we apply KCL to what we have here, if you apply KCL to this particular circuit, for T greater than 0, we know what is going on for T less than 0 and T equals 0 right now. But for T greater than 0, what is happening to this particular circuit? Okay, first of all, you want to find out. Let's say that the current passing through this R is IIR. So let the current passing through R be IR, right? So if the current passing through R is IR, what is the value of this particular current? We want to carry out KCL right now, but we must know the value of the current passing through this R before we carry out the KCL. Okay, so first thing you want to do is you say that, okay, let's apply KVL first of all. If you apply KVL, what would you have here? You would have minus VG, right? If you still remember our KVL, minus VG, okay, plus minus VG plus VR, and VR would be the same thing as IR multiplied by R. Okay, so plus IR, right, multiplied by R. Okay, let's say IR multiplied by R. This is this way, where IR represents the current passing through R. Okay, then it will be plus The other voltage we have here is the voltage across the capacitor plus V. Everything, if you add them together, should be equal to 0 according to KVL. All right. So if you rearrange what we have here and then you want to make IR the subject of a formula, all right, this would be equal to VG, right? VG minus V, all right, all divided by our R. Okay, so this will be by R. So this will be the current passing through this resistor here. IR will be equal to VG minus V all divided by R. Okay, so that is the current passing through here. All right, and then don't forget that we know that our VG is a step response, right? So VG for t greater than 0, VG would be equal to 1. Don't forget that, right? So this would mean that you can easily say that our IR would be equal to 1 minus V, right? 1 minus V all divided by R would be our IR in this particular case. So you have IR equal to 1 minus V divided by R. So we know this current right now. Now that we know the current passing through here, we can then go ahead and say that we want to try to find out our KCL. For KCL, you know that the current passing through here, for example, if you say that there is a current going, we usually have what we call a node. So you can have a node somewhere between these two elements here. Okay, so if you have a node, we know that KCL says that the current entering a particular node must be equal to current leaving the node, or the sum of all the currents around a node must be equal to 0. Okay, so for KCL, let's say there is a node. All right, if you remember how we deal with our capacitance, let's say there is a node somewhere here. You can see that for that particular node, on that node, we can say that there's a current IR going this way, and then another one current coming this way from that particular node. All right, and then what you find out is that for KCL, current leaving this particular node. Okay, sorry, this is supposed to be this way. Current is entering, IR is here. Okay, so this is IR entering this particular node. Current entering the node is going to be minus IR, right? It is entering the node, and this is going to be IC, by the way. Okay, so the current leaving the node will have a plus sign, so it becomes plus IC, isn't it? This would be equal to 0. These are the two currents that we are dealing with here. Don't forget, we said our IR is called 1 minus V over R. So what you would have eventually is going to be minus into bracket 1 minus V divided by R, because we found our IR. Don't forget, this is our IR. We found this here. So minus into bracket 1 minus V over R plus IC. Our IC is usually given as C divided T. Okay, so we know that. So that's where this came from. We discovered these and proved it in the previous classes we heard. You equate everything to 0. So eventually what you find out is that when you multiply it and you expand this becomes V minus 1. That is how we got this V minus 1 that you see right on top here. There's a V minus 1 right at top here. Yeah, so how we got this V minus 1 over R, if we expand this, it becomes minus 1 plus V over R, and that is how we got here. We have our C divided T here, and then everything equals 0. That's how we got that for KCL for this particular circuit when T is greater than 0. Now, so now that we know exactly what is going on here, we can then rearrange these to form or to look like a first order differential equation. When you do that, you obtain dB plus V over R equal to 1 over RC. Okay, so once you have this, we have to solve this to find out what, you know, the first solution would be, the triad first solution, and then the homogeneous solution. Okay, again, If you want to find out what the natural solution would be, this would become the Vn. Don't forget that we usually say that natural solution, you can represent the natural response as Vn. Okay, so this becomes the Vn, okay, plus Vn, all right, equal to this. Okay, so that would mean that you can assume that your Vn, you can assume the trial solution would be equal to K exponential St as we do normally, all right? So if you have it this way, and whenever you see Vn, you put this there. What you're gonna have left here will be Sk exponential St. You're gonna have that, then plus K exponential St over Rc. K exponential St over Rc. That's what you're gonna have. Everything will therefore be equal to 1 over R, 1 over Rc. All right. By the way, when you're talking about the natural response, we're going to forget about what we have here, this first constant. When we are talking about the natural response, this is going to be equal to 0, not equal to 1 over Rc, because 1 over Rc is like our first, constant here, okay, called first term. So this would be equal to 0, and then the usual thing we do is you have your K exponential St, because it's common to everything here. Then you have S plus, what do you have left here? 1 over Rc, right? Everything will be equal to 0. And then we already said that K exponential St cannot be equal to 0, because normally we should equate both of them to 0 and get two values. Okay, but K exponential St cannot be 0, so that means we can't equate it to 0. The only thing that can be equal to 0 is S plus 1 over Rc. Okay, so we say S plus 1 over Rc equal to 0. And from here, your S automatically becomes minus 1 over Rc. That's how we got S equal to minus 1 over Rc. Okay, so if you have that, what you have next would therefore be to try to find your Vn, because we already assume that our Vn is equal to K exponential St. So your Vn will be equal to K exponential S is minus 1 over Rc. So the minus comes here, and then 1 over Rc comes here, and then you still have your T here. Okay, so this becomes a natural response to this particular cycle function. So after that, you want to find your trial first solution. For the trial first solution, you assume that you can label it FBF, the first solution. You can say let it be equal to A. You choose any constant that you can work with and feel comfortable with. If it's equal to A, it simply means this becomes the VF, right, plus VF over Rc equal to 1 over Rc. So whatever you see VF, you put A there. This becomes dA to T. Everything here becomes 0 because d the T of A is a constant. It's going to be 0. So this goes. Then you're left with A over Rc equals 1 over Rc. You're left with A over Rc equals 1 over Rc. Okay, so Rc will cancel Rc, and all you're going to be left with is just going to be A equal to 1. And that is how they got this A here to be equal to 1. So the total response in this particular circuit will be equal to the trial solution plus the first solution plus the first response plus the natural response, or first solution plus the natural solution, or homogeneous solution, or characteristic solution. Okay, so if you combine both first and first together, just like I just mentioned, your V of T will be equal to, the first one will be A plus the second of which will be K exponential minus T over Rc. That's what you have here. Since our A is 1, you just put 1 here. And then this is our first solution. This is our natural solution, and this is the first solution. And then if you add all of those, this is what you obtain as your V of T, which is a solution to that particular circuit. However, what is going to be our V of 0 plus? Don't forget we said that at V of 0 plus, that would be the same thing as V of 0 minus, and that would be equal to 0 because we're dealing with a continuity principle. Okay, so in that particular case, what you can easily say is that when V of 0 is 0, that means T will be equal to 0. That would help us to find the value of our K because we need that value. So that would mean that V of T would be equal to when t is 0, v of t will be equal to 0. Okay, so if you put t to be 0, what you have left is just exponential 0. Exponential 0 would give us 1. K times 1 is k, plus 1 would be equal to 0 because this is 0. Okay, that's why t is 0 in first place. So k would be equal to minus 1. Okay, so if k is equal to at the end of the day, you find that k equal to minus 1 here. All right, because k plus 1 would be equal to 0. So if k is minus 1, you can come back and say, okay, we know the value of our k, we just put it back in here. This becomes 1 minus k, 1 minus exponential minus t over rc. Okay, or just minus exponential minus t over rc plus 1. Okay, so and that is exactly what we have here as our v of t eventually for t greater than 0. All right, so for t less than 0, of course, we know our vt is going to be equal to 0, but for t greater than 0, this is what we're going to have as the solution over there. All right, now what you can see here is once you write v of t here as v of t equal to this, you can say this is can be multiplied by 1. All right, everything multiplied by 1 is the same thing. This can be multiplied by 1. And don't forget, for our unit step, our u of t is always equal to 1 for t greater than 0. U of t is always equal to 1. So instead of just leaving it empty like that, you just put u of t here. So you know this is your v of t equal to this, and we know this is the unit step. Okay, we have to put this here because we're dealing with the step response. Okay, so this is key. Okay, again, if you want to sketch that, this is what it's going to look like for all the values of t, greater than 0. For all the values of t greater than 0, what do you have? You start with t equal to 0. Okay, for t equal to 0, you are going to obtain a value. This is when t is equal to 0, v of t has to be equal to 0. Okay, so that is why it's starting at the origin. Okay, you can see that that's why it's starting at the origin, and then you move on and say, okay, what happens when your t is equal to 1? When t is equal to 1, you have exponential minus 1 over rc here when t is equal to 1. Don't forget that our tau is always equal to rc by e. So you can take the exponential of all sides, and eventually you will find that your v of t will be equal to 1 minus 1 over e. All right, at the end of the day, you have that v of t equal to 1 minus 1 over e. And then if you have that here, what you eventually come up with would be when tau is rc, because you can replace this rc here with just tau. Okay, so when tau is rc, or when your t is rc, it simply means that your v of t will be 1 minus 1 over e, 1 minus 1 over exponential. This is just going to be e raised to power minus 1 at the end of the day. All right, and then you can go on and then keep going, keep finding the values of v of t for different values of t. We have an example for step and pulse response. It says find the pulse response of the following circuit and then sketch it. So you can see we have a circuit here. We have, how many sources do we have? We've got just one source, one independent source, which is the current source. We have a resistor connected in parallel with the inductor. The resistor has a resistance of 5 ohms, and the inductor has an inductance of 5 Henry. You can see the flow of current this way, all right? And then we're given I a function, the current function is given as current function is given as Ig of t, or I of t equal to 6 in this particular direction, in this particular dimension. Okay, so the resistor is connected in parallel with our inductor, and to make the work easy for ourselves, you will find out that when we're talking about real inductors or practical inductors, our resistance is, the load resistance is usually connected in series with the inductor. Now we want to take a KVL in this particular circuit. To make it easy for us to take that KVL, it's better for us to go ahead and connect and find a way to ensure that we find an equivalent circuit to this given circuit in such a way that the resistance will be in series with our inductor. So that is the easiest way, to simplify this circuit and then go ahead and carry out the necessary calculations and analysis. All right. So we could go back to where we started from, the Thevenin circuit we talked about the other time. If you remember, we said that if we have R Thevenin is always equal to R nothing, if you can remember that, right? And I also remember we said that when we are converting Thevenin circuit to Norton circuit, our VT is supposed to be equal to Rn, right? RNIN. Correct me if I'm wrong though, but I think it's supposed to be INRN. Yeah, if this is right, okay, we can use this to convert a Norton circuit to the Thevenin circuit, all right? From this here, this is going to be our Rn, as you know. So our Rn is going to be equal to 5 ohms. And the conversion sequence says that our Rn is equal to Rt. When we convert Rn to It, that simply means our 5 ohms for Rn will be same thing as our Rt, which would then be 5 ohms. So this is going to be, that's how we got this here. This is going to be Rt, by the way. This is Rt when you convert the Norton circuit to the Thevenin circuit. All right. Also, we need to find the VT. Okay. From what you can see here, this is going to be our IN. This is going to be our I Norton from the previous discussions we had when talking about this analysis. So to find our V Thevenin, now we want to convert this current to voltage. So to find our V Thevenin, it's going to be Rn multiplied by IN. Our Rn, we said it's 5. Our IN, from what you can see here, is going to be multiplied by IG of t, right? So all you have here is going to be 5 IG of t as our V Thevenin. Okay, so that is how we got this 5 IG of t here. So this is the equivalent, Thevenin equivalent of this Norton circuit here. So now that we have this circuit, so it becomes easier for us to say, okay, we want to take our KVL in this circuit right now. If you've got a loop like this, so if you take your KVL, you find out that the flow of this current, in this loop here, is going to traverse from negative to positive on this voltage source. So you have minus 5 IG of t plus 5I. The current passing through here is I. So the voltage here will be equal to 5 multiplied by I using Ohm's law. So 5 IR, which is I multiplied by 5, and that gives us 5I. Also, the voltage across the inductor, or the voltage induced here in this inductor, will be L di the t. Okay, voltage is going to be L di the t. Okay, so if it's L di the t, what is our L? Our L is going to be 5. So that's how we have this 5 di the t here. This is going to be IR according to Ohm's law. And then according to KVL, Kirchhoff's voltage law, the summation of all the voltages in that loop would be equal to 0. So you add everything together to give us 0. So when you do that, you can rearrange it and then you have something like this, and you can label that equation 1. So if you have your equation 1 labeled, the next thing you want to do is to begin to analyze from our continuity principle. We do know that I of 0 naught will be equal to I of 0 minus, which will be equal to I of 0, which is equal to I naught, by the way. Okay, so this represents our continuity principle that we've been talking about. What you want to do quickly here is to find out what is happening from t greater than 0 and t less than 1. From t greater than 0 and t less than 1, what is going on, right? We said that our Ig of t will be equal to 6. Okay, when t is greater than 0 and t less than 1, this is like going to be a unit. If you can remember some of the conversations we had in the previous classes, u of t minus u of t minus 1 will be equal to a unit function. Okay, so let me quickly take us back to that so that we can all be on the same page. If you go here, excuse me, let me clean this up. So if you go here, you will find out that when we're talking about our functions, so we said that when we have a u of t minus u of t minus t naught, all right, this will give us, in the post function, this will be equal to 1. And you see that here. All right, so the graph tells us that u of t minus u of t minus t naught, when t is greater than 0, okay, and less than t naught, this would be equal to 1. This is very, very important for us. Okay, so With that in mind, we can easily represent that in the particular, equation that we have and say, okay, from this particular question here, this here, this would be equal to 1. All right. In this particular case, the T naught we have here is 1. In this particular case, this is representing T naught. Okay. So that is why we are saying, okay, for T greater than 0 less than T naught, or T greater than, and T naught is 1 by the way. So it becomes T greater than 0 less than 1. All right. This entire function here is going to be equal to 1. So our IG of T would be equal to 6 times 1, and that is how we got this 6 that we have here. All right. So if we take it a step further from there, from this equation 1 here, you can easily substitute your IG of T to be equal to 6. If you do that, you have the IDT plus I equal 6. And as soon as you are able to pinpoint that you have that, the rest becomes very easy to deal with. The rest is just going to be basic simples plus mathematics. Okay, first of all, you want to find your characteristic equation as our man is. So to find characteristic equation, the I, the T, the coefficient of this will represent S. Right, so we have S plus 1 equal to 0, and then from here our S will be equal to minus 1, and the natural response of the circuit will then be equal to, normally it's supposed to be K exponential ST. So since we found our S to be minus 1, if you put minus 1 here, it becomes K exponential minus 1t, or K exponential minus t. So this becomes the natural response of that particular this particular circuit. So we get the natural response from the characteristic equation, and this is like In, by the way. We have S plus 1 equal to 0 here, and then we have our natural response In will be equal to K exponential minus 6. So we keep this somewhere. Now to find the first solution, we'll find a trial first solution IF. You say let IF be equal to A, or you can say let it be equal to any kind of constant that you want. So let IF be equal to A. So whenever you see I, you put IF there. And if IF is equal to A, you can also replace IF with A. So you have the A, the T. A is a constant. Why are we saying let the first solution be IF? Let the first solution be A rather. It is A because A is just an arbitrary constant. And what you can see here, the first, the first term we have here is a constant. That is why we are saying that let A be equal to let the first, trial first solution be equal to a constant A. All right. In some cases, when as we go further in our studies, we'll find out that when this term here is not a constant, you cannot just say let IF be equal to A. If it's a trigonometric function we have here, there is going to be IF would be equal to a trial, solution which is trigonometric function, not just a constant. If this were to be an exponential function, IF would be equal to an exponential, first solution. The first term here is a constant, so that's why we are saying let IF be equal to A. Okay, so if that is that, we have the A, the T is going to give us 0. And then if IF is A, this becomes IF, it becomes A. So our A automatically will be equal to 6. So if A is equal to 6, we keep that somewhere too, and then we can continue our analysis. Okay, so keep that somewhere and let's go on. A is equal to 6, and then since our IN is KE minus T, the total solution will be the first solution IN plus, the natural solution IN plus the first solution IF. That is what we have. So it becomes KE exponential minus T plus 6. That becomes our total solution for the particular circuit. All right. Then we know that I of 0 minus, which simply means what is happening in the circuit before the switch is turned. Before the switch is turned, what is going on in the circuit? All right. So I of 0 minus is going to be equal to 0 because we know I of 0 minus, like we defined it here for continuity. I of 0 minus is same as I of 0 plus, which is same thing as I naught or I of 0, and that is going to be equal to 0. Okay, so we have K exponential minus T plus 6 equal to I. So if I is 0, it means our T is 0 because it's I of 0 that gives us 0. So that means I of 0 is 0 when T is equal to 0. So if you put 0 here, you have just K left. So you have K because T is 0, exponential 0 is 1. 1 times K is K. So you have K plus 6 will be equal to 0 because I of 0 minus is 0. So K will be equal to minus 6. All right, these are important stuff. So in k is equal to -6, then you can go back here and say, okay, your total solution becomes -6 exponential minus t plus 6. And if you rewrite that, you can, it gives you 6 1 exponential 6 into bracket 1 minus exponential minus t for t greater than 0 less than 1, right? And then you put the union ampere here. All right, so that is for when you have t greater than 0 and less than 1. This is going to be the response, total response in the circuit. All right. So what happens when t is greater than 1? When t is greater than 1, what happens? If you go back to the first function I gave you, when t is greater than, what we had was, we had something like this. We had something coming this way, and then we go up, we go this way, we come this way, we go this way. Okay, so this is 1 here. This is our I, and then this is t. All right, and then we have this is t0. We have this is t is got 0 here, and then we have a value of t here. All right, so and when this is for t greater than 0 less than t naught, where t naught is 1 in this particular case. Okay, so anything greater than 1. Okay, so this is 1, this is 0 from this particular function we have, first function we have. So this is t here. So anything greater than 1 simply means that our I will be 0. Okay, when t is greater than 1, from what you can see here, our I, okay, anything greater than 1, our I will be 0. Okay, that's what it simply means. So for t greater than 1, I g of t will be equal to 0. So from equation 1, I of t, I g of t is equal to 0. You are left with the I to t plus I equal to 0. From here, what do you find out? You can assume your natural response In is going to be equal to k exponential st. If you put that in here, you obtain characteristic equation s plus 1 equal to 0. Your s will be equal to -1. If s is equal to -1, then your I of t would be In of t. This is natural response, and that would be equal to k exponential minus t. All right, this is very important. Since we have the I, the t plus I equal to 0 when t is greater than 1, it simply means that there is no point finding a first solution. There's no point finding a first solution because we already have this equal to 0. So all we are dealing with is just going to be characteristic, term. Okay, no forcing function at all is going to be derived in this case. So our initial condition I of 1 plus will be equal to I of 1 minus. All right, so and that will be equal to I of 1, by the way. So that simply means that wherever you see your t, you put 1 there. All right, so you have 6 into bracket. We are picking this up. Where is it here? This is the total solution we obtained here for the initial conditions here. Where is it here? This is it. For the initial conditions, this is exactly what we obtained. Okay, so I of t equal to 6 1 minus exponential minus t. Okay, so in this case, when t is greater than 1, the initial condition becomes I of 1 equal to 6 1 minus exponential minus 1. And what we will obtain when we do that is going to be 3.79. So we have I of 1 will be equal to 3.79. Now that 3.79 we obtained tells us that we have obtained this value to be 3.79 for the initial condition. Okay, so that means k exponential minus 1 that we obtain here will then be equal to the initial condition value 3.79 that we obtained. If you do that, you obtain your k equal to 3.79 multiplied by e. All right, so if you have these, your total I of t therefore becomes I of t equal to 3.79 e exponential minus t. So you have e dot exponential minus t. Okay, so when you have that and then you want to simplify this, it becomes just e 1 minus t. It becomes e 1 minus t. If you still remember your mathematics properly, or e minus t plus 1. That is exactly where they got this from. For t greater than 1, for the time function greater than 1, this is what they're going to obtain. The next thing you probably want to do is to sketch the function. Okay, so sketching the function becomes very easy. For t greater than 0 less than 1, all right, this function here is going to be 1. So our ig of t is going to be equal to 6 that we found out. So eventually you see that this is going to be 6 here. There's going to be 6 here. If it were to be ig of t equal to just u of t minus u t of minus 1 without the 6 here, then this is going to be 1. But since we have 6 here, 6 multiplied by 1, we have 6 here. So this becomes your first function for this particular circuit. And then from the equation that we obtained, if you flip back a little bit, you got 6, 1 minus exponential minus t. So for the values, this is for t greater than 0, less than 1. So for all values of t between 0 and 1, to plot it into this particular function, you will get a curve from 0 until you get to 1. If you connect all the dots together, you get different values for 0.1, 0.2, 0.3, 0.4, right up to 1. And then you keep getting different dots here. When you do that, you connect for different t's between 0 and 1, you keep getting different currents. So if you and that will give you different dots. When you connect all the dots together, you get this particular curve. Again, for t greater than 1, you notice that we got this particular function. So for all values of t greater than 1, 1.1, 1.2, 3, 2, 3, 4, until we get to this particular point where I of t equals 0. You keep getting different values of current, and then you can have different dots. You connect all the dots for different values of t. This is the kind of curve that you're going to obtain at the end of the day. Okay, so this is how you obtain you sketch the curve for this particular circuit. All right, so this is also straightforward because these are things we've done before.